Okay, in previous sessions we have discussed the normal distributions. So first of all, we start with the summary what we have discussed in previous sessions. This normal distributions, which is a continuous distributions, and there are four types of continuous distributions: normal, exponential, gamma, and chi-square. And normal distributions, which is symmetric. Okay, most results are located in middle, and few are spread both the sides, and which is a bell shape, and can entirely described by mean and standard deviations. Okay, and which is useful to interpret and analyze statistical data. And here we have defined normal distributions as f of x equal to 1 upon sigma root 2 pi e raised to minus 1 by 2 x minus mu upon sigma square. Okay, where x in between minus infinity to infinity and mu in between minus infinity to infinity, sigma is greater than 0. So mu and sigma, which is our mean and standard deviation, we call it parameter of a normal distributions. Okay, and the curve we call it a normal curve. So in between any interval, if you want to find out the probability of x between x1 and x2, then by normal distributions, here f of x dx over x1 to x2, but f of x is 1 upon sigma root 2 pi e raised to minus 1 by 2 x minus mu upon sigma square. Okay, and what it means? It means according to our graph of figure, if you see, then there is x1 and x2 here, and so in between the probability in between x1 and x2, it means the area between x1 and x2. Okay, in this interval for a given curve, normal curve. Okay, so and we convert this normal distributions into a standard normal distribution, and here we are discussing some properties, bell shape, symmetric, and all this which we have already discussed. Here for normal distributions, mean, median, mode are equal, and total probability under which is minus infinity to infinity, f of x dx equal to 1, and f of x which we already know, and then x equal to mu divides the area under the normal curve into two equal parts. Okay, so that's the as x equal to mu, which divides all normal distributions into two equal parts. Okay, and because of the symmetricity. Okay, so minus infinity to mu f of x dx is equal to f of x dx mu to infinite is equal to 1 by 2, and f of x is always negative for all value of x. So the whole curve which we get the above x-axis. Okay, and we have seen that there's most of the region in between mu minus sigma plus mu plus sigma, which is 68.27%, and mu minus 2 sigma, and region between area between mu minus 2 sigma and mu plus 2 sigma is 95.45%, and area between the ordinates at mu minus 3 sigma and mu plus 3 sigma is 99.74%. So almost all regions which cover by this interval mu minus 3 sigma to mu plus 3 sigma. Okay, and parameter, and we have already seen this expectations of normal distributions, which is mu, and as we know that mean, uh, median and mode also you get mu, and so by mathematically you also can say that the given distributions is symmetrically. And okay, these things which we have already discussed, now deal with difficult. So what we do, we convert this standard normal distribution to into a standard normal distributions. So we consider z is equal to x minus mu by sigma. Okay, which is a new random variable, and e of z, if you find out, then we get 0, and variance of z is 1. So distributions of z is also a normal here, and so and mu mean we get 0, and standard deviations 1 for the standard normal distributions, and which is okay. And here we call it z as a standard normal variant. Okay, and see you can see that this, if you have to say that find out for p of x in between x1 and x2, which is exactly same as p of z in between z1 and z2. Okay, so here z1 is x1 minus mu upon sigma, and z2 is x2 minus mu upon sigma. a normal variant to a standard normal variant, then our graph in which I get the mu as y-axis here. So mu is equal to 0, and this graph which is symmetric along y-axis. Okay, here now here which is symmetric along any x equal to mu. Okay, but here we have mu equal to 0. So here we have mu equal to 0, and we get the graph of a standard normal curve which is symmetric along y-axis, positive y-axis. And we have discussed different case when we're dealing with the standard normal variant Z. If both Z1 and Z2 are positive, then area between probability of Z greater than 0 less than Z2 minus probability of Z greater than 0 less than Z1. Okay, so area under the normal curve from 0 to Z2 minus area under the normal curve 0 to Z1. And how we get this? You can see that this is by the standard normal table. We have a value for the area between 0 to Z. Now here 0 to Z2 if I take, then we get all this area, but we want to find out only this area. So what we do, we subtract this area 0 to Z1. Okay, so first we take the whole probability of Z in between 0 to Z2 and then subtract this 0 probability of Z greater than equal to 0 less than equal to Z1. And if Z1 less than 0 and Z2 greater than 0, it means Z1 is negative. So here minus Z1. Okay, I call it minus Z1. It means so Z in between minus Z1 and 0 and Z greater than 0 and Z2. Okay, so now because of the symmetricity along y-axis, this whatever area we get in between minus Z1 to 0, which is same as the area between 0 and Z1. Okay, so we can also write these two are equals. So I get now probability of Z in between 0 and Z1 and plus probability of Z in between 0 and Z2. So area under the normal curve from 0 to Z1 plus area under the normal curve 0 to Z2. Okay, so these things which we have here, this minus Z1, whatever area we have here, just what this distance 0 to minus Z1, same distance we have to take here 0 to Z1, and again you get some area. So and already you have 0 to Z2, so summation of these two area in which you get. And why we are taking 0 to Z1, as we know that in our normal table we have a value for a positive Z. Okay, now some other cases like p of x greater than equal to x1. So if Z1 greater than 0, then p of Z, now see, we can convert into a standard normal variant. So p of x greater than x1 is equal to p of Z greater than Z1. But Z1 which is greater than 0, then we can find out by 0.5 minus p of Z greater than equal to 0 Z1. As we know that, see, Z greater than Z1, it means this area Z greater than Z1. All this here in this line we have all Z which is greater than Z1, and under the curve we get this area. Now we want to find out this area. So as we know that this whole area on the right side of y-axis which is 0.5, so it means we have to subtract this area 0 to Z1. Okay, so 0.5 minus probability of Z greater than equal to 0 less than equal to Z1. Okay, now Z1 less than 0, then it means p of Z greater than equal to minus Z1. So Z1 less than 0, it means all this area. Z1 less than 0, it means somewhere here. Okay, and so we want to find out the region or area of all this, and we already know that right hand side we have this area which is right hand side of y-axis which we have 0.5. Now we want to find out this area only, but because of the symmetricity, whatever area we get here which is same as in between 0 and Z1. Okay, here somewhere if I have Z1 here some minus Z1, so similar way we get here some Z1. So what we do, from 0.5 plus Z p of Z greater than minus Z1 less than 0, which is same as p of Z greater than 0 less than Z1. Okay, so we may deal with z according to the situation in other case also. And this standard normal table which we have already discussed previously. Okay, so and which you have always given for any z greater than 0. Okay, so this use of normal distribution, which is approximate to binomial Poisson distributions, which is also extensively used in sampling theory and finding the confidence of limit of a parameter, so which we will discuss, and testing of statistical hypothesis, all these things which we will discuss in applied statistic unit 4. Okay, and then we have discussed one example. Okay, last time we have already discussed this example, and here we have find out for p of z greater than 0.109, and now this z greater than 1.09. So we want to find out all z we have here greater than 0.109. So we want to find out this area. But if I want to find out this area, what I do, as we know that all this area along right side of y-axis, which is zero point 0.5. So I will find out z in between, area in between 0 and 1.09, and I will subtract from 0.5. Okay, so I have find out this, and how we get for this 0.3621, which we get from the table. We have to look at in the first column at 1.0, and then in row 0.09, whatever value we get, which is 0.3621. So now everybody know how to look in the normal table. Okay, so 5 minus this, and which we get z greater than 1.09. Now p of z less than equal to minus 1.65. Okay, so z less than minus 1.65, minus 1.65 some here, and all z less than, it means left side of minus 1.65. Okay, and so if you look at here, so we want to find out this area, but because of the symmetricity, I have to find out like area here. If we can see that which is nothing but, if I draw a line here, then 0, this is the right hand side whole 0.5, and I have to subtract this 0 between z greater than 0 less than 1.6, probability of z greater than 0 less than 0.6. So area between 0 and 1.65, I have to subtract from 0.5, and from this, which is also you can look at as whole area is 1, and I have to subtract from 1 this all z greater than minus 1.65. It means all this area I have to subtract. But again, we can't use this by z greater than minus 1.65. For that, we cannot use the in a table. If I want to apply the value from the normal table, then my z must be greater than 0. So what I do, I convert like first I write all this area 0.5, and then I use the symmetricity and subtract this area p of z greater than 0 less than 1.65 from 0.5. So I get all this area. Okay, so this is 0.0495. Now z in between minus 1 and 1.96. Okay, so now here one z is your negative and one is positive. Okay, so this in between 0 and 1.96 you can easily find out. Okay, but now with minus 1 to 0, so we have to use symmetricity and add in whatever area we get, we have to add this area. So see, you can represent this minus z greater than minus 1 less than 1.96 as probability of z greater than equal to minus 1 less than equal to 0 plus probability of z greater than equal to 0 less than equal to 1.96. Now this minus 1 to 0, but we have to convert into a positive value, so we use the symmetricity, which is the probability which is same as z greater than equal to 0 less than 1. Okay, and here z greater than equal to 0 less than or equal to 1.96. Now again you have to look in z table at 1.00, so for which you get 0.313, and again into z table you have to look at 1.96. So in first you have to look for 1.9, and then in a column 1.006. So you get this value 0.4750. Okay, so this is 0.81, sum of this 0.8163. And fourth one, z in between 1.25 and less than equal to 2.5. So here both z1 and z2 are positive. Okay, so we want to find out this area. So what I do, I will find out area between 0 and 2.75 and then subtract this 0 and 1.25. So probability of z greater than 0 less than equal to 2.75 minus probability of z greater than 0 less than 1.25. So these things 2.75 you have to look in the table and you get this value 0.4970 and here 1.25, so minus 0.3944, so 0.1026. Okay, we have already discussed the z table in previous session, so you know that how to find out the value from the z table. Okay, now, so all these things which we have discussed right now, which we have already discussed in the previous session, now in today's sessions we are start from the example number 2. So if x is a normal variant with mean 30 and standard deviation 5, find the probability of x which is greater than equal to 26 and less than equal to 40 and x greater than equal to 45. See, here we have given mean and standard deviation. So mu and sigma which we have already given. And we want to find out the probability of x greater than equal to 26, less than equal to 40. So this x1 and x2 we have given. Now we have to convert it into a z1 and z2. So try yourself first and reply me your z1 and z2 for this first one. Okay, first example. Probably. So here find out z1 and z2. Reply your z1 and z2 in chat box. Okay, so x in between 26 and 40. Mean is 30 and standard deviation is 5. So find out z1 and z2. See, you have to find out x minus mu upon sigma. So z1 is equal to your, here x1 you have given x1 minus mu upon sigma. Reply your z1 and z2. Akanksha, Kumar Pal, reply your z1 and z2. Parth, what you get here? Z1 is equal to, see, just z1 you can find out by x1 minus mu upon sigma. X1 you have given 26, mu you have given 30, and sigma standard deviations you have given 5. So it means 26 minus 30 upon 5. Okay, standard deviation you have given 5. Okay, so x minus mu upon sigma, so 26 minus 30 upon 5, and which is you get minus 4 by 5. So minus 4 by 5 it means minus 0.8. Is it clear? Now similar manner you can also find out for 40. So this minus 0.8 is my z1. This is minus z1. And what we get now for z2? 2. Okay, so which I get 2 here. 40 minus 30 by 5, 10 by 5 is equal to 2. So probability between of x in between less 26 and 40, which is nothing but probability between z minus zero point 0.8 and less than equal to 2. So probability of z greater than equal to minus zero point 0.8 and less than equal to 2. So these both are equal as we have here. Find out. Okay, this is minus zero point 0.8 and 2. Now how to deal with this? Z in between minus zero point 0.8 and 2, it means this area we want to find out. Here we have minus zero point 0.8 and 2. All this area we want to find out. Now this 0 to 2 we can easily find out for Z table. Now here we use the symmetricity of a normal curve. So we have to add this 0 to zero point 0.8. Okay, probability between 0 and 0.8. So this is minus 0.08, z in greater than equal to minus 0.08 and less than equal to 2. So which we can represent by z greater than equal to minus zero point 0.8 less than equal to 0 plus 0 plus probability of z greater than equal to 0 less than equal to 2. Now use the symmetricity here. So I get probability of z greater than equal to 0 less than equal to 0.8. Now this 0.8, which you have to look in the table. So I get this 0.2881. See, I have already attached the normal table with this meeting. So you can open the table and you can look at this value 0.8. Okay, 0.8, which you get 0.2881. Okay, and z equal to 2. So for that you get 0.4772. Okay, so you have already a z table. I have already attached with this meeting. You can download it and look it in the table, so you get this value. Okay, so whenever next time you come, you have to come with the printout with the z table. Okay, and sum of these two, which I get 0.7654. So anyone have doubt in this example, you can ask right now. Okay, reply in chat box if you have doubt. Everyone is clear? Okay, fine. So now next thing we have to say that find out p of x greater than equal to 45. P of x greater than equal to 45. So first try yourself. First try yourself and find out the probability of x greater than equal to 45. Okay, I give you 2 minutes. Try yourself. So here you get z equal to 3. Okay, so it means you have to find out the probability of z greater than equal to 3. Okay, Nancy get 0.0013. Okay, so now see, if you want to find out probability of z which is greater than 3, then you want to find out this area. So what we do, we subtract from point. All this area is 0.5 on right side of this y-axis, okay, which is whole 0.5, and I subtract this 0 to 3 area from between 0 to 3, okay, under the curve. If I subtract, then I get this v of z greater than equal to 3, okay. So 0.5, and then so I get 0.0013, so correct, okay. Now a manufacturer known from his experience that the resistance of resistors he produce is normal with mean 100 ohms and standard deviations is equal to 2 ohms. What percentage of resistors will have resistance between 98 ohms and 102 ohms? Okay, so resistance of a resistors he produce uh, for is a normal with mean 100 ohms and standard deviations 2 ohms. So we have already given mu and standard deviations. Okay, for normal variant x, mu is equal to 100 and standard deviations is equal to 2. Now, what percentage of resistors will have resistance between 98 ohm and 102 ohm? So probability of x in between 98 and 102. So first we convert this x1 98 into z1. So x minus mu upon sigma. So 98 minus mu, it means 100 upon 2. So minus 2 by 2 is equal to minus 1. Z1 is equal to minus 1 and x is equal to 102. So x minus mu upon sigma 102 minus 100 by 2. 2 by 2 is equal to 1. So this your z probability. So it means you want to find out the probability of z between minus 1 and 1. Okay. So now this minus 1 and 1. So first 0 to 1 probability of, so which is probability of z between minus 1 to 0 plus probability of z which is in between 0 and 1. Okay, and then you have to use the symmetricity. So my z in between minus 1 to 0, which is same as z in between 0 and 1, and then from the normal table you get, see, for 1 you have to see, you have to find out the value in a normal table, which you get 0.3413, and here also 1, so same, which is 0.3413, and sum of this, which is our area under the curve here between minus 1 to 1. Okay, so this is the probability of x greater than equal to 98 less than equal to 1 0. Now but see, we have to say that find out what percentage of resistors, okay. So the percentage of resistors, which is 68.26%. okay. From this you have to multiply it with 100 and convert into a percentage. Okay, now example number 4. The average seasonal rainfall in a place is 16 inch with standard deviations of 4 inch. What is the probability that the rainfall in that place will be between 20 and 24 inch in a year? Okay, so average rainfall we have given 16 inch. It means mu we have given in standard deviations, which is 4, and we have to say that find out the probability that rainfall that place will be in between 20 and 24 inch. Okay, so probability of x greater than 20 and less than equal to 24. So first we convert this x1 and x2, 20 and 24, into a z1 and z2 by using this mean and standard deviation. Okay, so 20 minus mu, it means 16 upon 4. So 4 by 4, 1. I get 1 here. And for 24, x minus mu upon sigma. So 24 minus 16 upon 2. So this is 8 by 4. I get 2. So now my z, probability of z in between 1 and 2. Okay. So probability of x greater than 20, greater than equal to 20 and less than equal to 24, which is same as probability of z greater than equal to 1, less than equal to 2. So in between 1 and 2, so now both are positive. So what we do, we find out between 0 and 2 first, probability of z greater than 0 and 2, minus, we subtract this portion. So I get this region, area between 1 and 2. So from 0 to 2 minus 0 to 1. So I get in between 1 and 2. So 0.4772, which I get from the table. I have to look for z equal to 2 in a z table. So I get this minus 0.341 for z equal to 1. Okay. In subtractions, which give here, which we get 0.1359. So this is our answer. Okay, so the probability that the rainfall in that place will be between 20 and 24 is 0.1359. Now, some important notes. So after dealing with the previous example, let's make some important informations here. Suppose probability of x less than x1, so which is nothing but the f of x1 cumulative. Okay, this is a continuous distribution, so cumulative distributions, which we get minus infinity to x1 f of x dx, which we get minus infinity to x1 f of x dx. Now hence p of x less than equal to x1 represents the area under the curve x equal to minus infinity to x equal to x1. Okay, and now this p of x less than equal to x1, which is less than 0.5, less than 0.5, then the point x1 lies on the left of x equal to mu. Okay, as we know that at x equal to mu, normal curve divide into two equal parts. So if your probability of x less than equal to x1, which is less than 0.5, then, and which is in between -1 to x1, and this probability which we get less than 0.5, then I can say that this x1 is a negative. Okay, see, you can see here is this x equal to mu, which divide into two equal parts. Now if I get point, see, greater than 0.5, then hold this 0.5. If the some x1 is somewhere here, then 0.5 plus some area we get. But see here, I get p of x less than x1, which is less than 0.5. Less than 0.5, it means we get a line between any point in between 0 and minus infinity. Okay, so I get this z or which x, which is less than 0, negative. So whenever p of x less than equal to x1, which is less than 0.5, then your x1, which is a negative. In similar way, you look for a standard normal variant. See, for standard normal variant, this is your z equal to 0. Okay, z equal to 0. So whatever z you get here, which is z equal to minus z1, which is negative. Okay, and here this is because this region is 0.5. If which is greater than 0.5, then from this minus infinity to x1, which is greater than 0.5, then which cover whole this portion, and then another part of here, but which is not a case here. Here we have a probability of x less than x1. Okay, so in this case we always get the corresponding standard normal variant z, which is negative. Okay, we cannot say about x1, but z is always negative. If we convert into a standard normal variant, then we always get z as a negative, because we cannot say about x1, because it might be a mu or whatever at any point. Okay, so we cannot discuss about the x1, what is the x1, but we can say that z1 is always negative if we have p of x less than x1. Okay, which is less than 0.5. Now if this probability of x less than x1, which is greater than 0.5, then x1 lies the right of x equal to mu, which is right of x equal to mu, and the corresponding standard normal variant you always get positive. Okay, and you can see here, see, this is right on greater than 0.5. So this whole regions here, which is 0.5, now greater than 0.5, it means some, it also add this region somewhere here point. So I get z is always positive. standard normal variant Z1 is positive for P of x less than x1, for which I get probability greater than 0.5. Okay, I will use this in an example. Okay, we are going to use this information in next example now. So I hope everyone is clear. This, whenever you have P of x less than x1, it means probability of x less than x1 and which is less than 0.5, then your standard normal variant which is negative, and probability of less than x1 which is greater than 0.5, then your standard normal variant which is positive. Now if x is a normal variant with mean of 120 and standard deviations of 10, so find C such that P of x greater than C is equal to 0.02 and P of x less than C is equal to 0.05. Okay, so x is a normal variant with mean 120 and standard deviation 20. So mean mu is equal to 120 and standard deviations we have given. And x greater than C, probability of x greater than C is equal to 0.02, which is also given, and we want to find out the C. Okay, so first we look for first one, P of x greater than C. Okay, so first we convert into a standard normal variant, and so we write this, but we don't know about x right now. Okay, so what we can say here, C minus, this is standard normal variant, z is equal to x minus mu upon sigma, and mu we have given 120 and deviations we have given 10. Okay, and probability of x greater than C which is 0.02. So probability of x less than C, from this what I can say, that if probability of x less than C is equal to 1 minus probability of x greater than equal to C. Okay, and which we have given. Now probability of x greater than C or greater than equal to C both are equal, because this which represents the area greater than C. If I include C, then also there is no difference between this area. Okay, so and generally this which we find out by the integrations area under the curve, and we know that this is the approximate area. So this 0.02 which is same as for P of x greater than equal to C. So 1 minus P of x greater than equal to C. Okay, we can say that P of x less than C we can represent in this manner, 1 minus P of x greater than equal to C, but which we have given 0.02. So I get 1 minus 0.02 is 0.98. So P of x less than C. Why we have find out this P of x less than C? See, in previous notes we have discussed this. If P of x less than x1 and which is greater than 0.5, then my Z1 is positive. So here we get 0.98 which is greater than 0.5. Okay, greater than 0.5. So I can say that my Z1 is standard normal variant is positive. Okay, you can see that this is P of x less than C greater than, and we have given notes for x less than C here, not for x greater than C. Okay, so we have discussed the notes P of x less than x1. Okay, so here that's why I have convert this P of x less than C and 1 minus P of x greater than equal to C. So my Z is positive. Once I know that Z is positive, it means somewhere here. Okay, I call it Z equal to Z1, and these regions, okay, so these regions which we have to discuss. Okay, Z positive I get. Okay, fine, and I want to find out the C. This x Z equal to, once we get Z1, then from Z1 we can find out the C. So x greater than C. Okay, P of x greater than C, it means P of Z greater than Z1. X greater than C here, x greater than C, it means Z greater than Z1. And x greater than P of x greater than C, which we have given 0.02. Now Z greater than Z1, so all this right hand side which is 0.5, all right hand side is 0.5, and I have to subtract this 0 to Z1, 0 to Z1 from 0.5. So 0.5 minus probability of Z greater than equal to 0 less than equal to Z1. Okay, and now see simplifications. write this is on right hand side and this one is on left side. So 0.5 minus 0.02, which I get 0.48. Now I have to look in the table, where in the table we have 48. Okay, 48. Now reverse way we have to think here. For in a table, see, generally we, by using Z1, we want to find out the value for uh, normal from standard. Okay, no, from the table, standard normal table, we find out the value for probability of with area under the curve between Z and Z1 by using Z1. But now by using this value, we want to find out Z1. Okay, so you have to find out the value this 48 in a table, and from that you have to find out this Z1. Okay, where it's situated in a table, which you have to find out. Okay, so from table, and then you get 2.05. Okay, might be approximate along 0.0005. I show you in table like this is 0.48. Okay, this is 0.48 in a table. If you look, 0.48, this is 47 and 48. Now see here, 0.4798, and then we get 0.4803. So now this is in the 2.0, and where it is. So, and see, this one is near to this 0.798, which is near to 4800. Here we have difference 0.03, and here only 0002, 0.0002. So this value, which is near to 0.48. Okay, so this 2.0, and now we have to look this column. So which is 0.04798, which is situated in column 0.05. So actual value you get 2.05. Okay, so 2.05. Is it clear? So now once we get Z1, from Z1 now we have to find out C. Z1 is equal to C minus mu upon sigma. Z1 is equal to C minus mu upon sigma. Mu we have given 120, sigma is 10, and this Z1 we have already find out 2.05. So C minus 120 upon 10. So I get C is equal to, now after simplification, 140.05. So if you have any doubt in this example, then ask me. First, look at what we have do here. Okay, we have to say that find out for P of x greater than or equal to C. We have given which is equal to 0.02, and we have want to find out C. And this data we have given. Now we have already know that if P of x less than x1 and which is greater than 0.5, then x1 is positive. So we use the previous note here. Here x less, we have discussed for x less than C, and which is nothing but 1 minus P of x greater than or equal to C. Okay, which we can, as we know that whole area under the curve, which is 1. Okay, sum of all probability, which is 1, and x less than C, so it means I have to subtract this x greater than or equal to C. Okay, so 1 minus 0.02, and these things we have given 0.02, and I get 0.98. So it means P of x less than C, which is 0.98, so which is greater than 0.5. So I get Z is positive, and then P of x greater than C. Okay, whatever we have given is x greater than C is equal to P of Z greater than Z1. These two are equal, as we know that. So, and which we have given here 0.02, and this can be represented from the graph. You can see that 0.5 minus 0 Z1, and so from that I get 0.48. Now from the table Z1 you get 2.05, and once you get Z1 you can find out C here. Okay, Z1 is equal to x minus mu upon sigma, and x is equal to C. Okay, how we find out Z from table? Okay, fine, good. See, we have given this probability of Z greater than or equal to 0 less than or equal to Z1 is equal to 0.48. Okay, now 0.4800. It means 0.48, it means 0.4800. Now if we see in the table, if we see in the table, then I have to look out in this table at 0.4800. But see, once I find out here 0.4798 and 0.4803, so there is no any point at we get 0.4800. But now this point 0.4798, which is near to 0.4800. Okay, so I can consider this value. So for this, okay, what I have to look at here in this row, which is 2.0, and then I have to add the whatever point in first point in this column. Okay, so which is 0.05, 0.05. So 2 plus 0.05, which I get 2.05. Okay, this is 0.4798, which is near to 0.4800. Here see we have 0.4803, but here we have difference of 0.0003, and here we have difference of 0.0002. So I will consider this point. Okay, so I get 2.0, and then look at this column, then which is for 0.05. Okay, 0.05. So I get 2.05. I hope it is clear now. Pass. Okay, so I get Z1 is equal to 2.05. So now try yourself and discuss for P of X less than C. First try yourself. Second one. Okay, I give you 2 or 3 minutes. The second one, P of X less than C is equal to 0.05. So here you have directly given this probability, which is 0.05 and less than 0.5. Less than 0.5, it means your Z1 must be negative. Okay, so you have find out 1.64. Let us see. So here you can directly say that P of X less than C, which is less than 0.5. Okay, is 0.05, which is less than 0.5. So your Z will be negative. Now negative here. Okay, so and your X less than this C, it means your all Z which is less than Z1. Okay, this minus Z1. So this area you want to find out, which you have given 0.05, and you want to find out this Z1. But now this is the same as this 0.05. Okay, so use the symmetricity. So Z1 we get here somewhere. P of X less than C, it means Z less than minus Z1, but which is 1 minus P of Z greater than equal to minus Z1. Greater than equal to, it means this one. And so this can be nothing but 0.5. See, once again, X less than C, probability of X less than C, which we have already given 0.05. Okay, now Z less than minus Z1, as we know that Z is negative. So this is somewhere here I get this negative minus Z1. Okay, now and all Z which is less than Z1, so this area, okay, which is I have given 0.5. So if I look at this whole graph, which is 1, And so from 1 minus this one, 1 minus this p of 1 minus this one, p of z greater than minus z1, then I get this area. This area is 0.05, and which I get as whole is 0.1. And if I subtract this remaining all this portion, remaining all this, it means my z greater than equal to minus z1. Now z greater than minus z1, it means, now see, remaining all this, it means this on right hand side of p of z, this right hand side of this y-axis, which is 0.5, which is 0.5, and this is in between, z in between minus z1 and 0. Okay, here which is minus z1 and 0. So 0.5 plus z in between minus z1 and 0, and which we have to subtract from 1, then I get 0.05. Okay, now here we are going to using symmetricity. Z in between minus z1 and 0, it means z in between 0 and z1. Okay, and so 0.05. Now if I subtract 1 minus 0.5, so I get 0.5, and then minus p of z between 0 and z1. So p of z between 0 and z1, which is 0.5 minus 0.05, which is 0.45. Now 0.45, I have to look in the table, 0.45. Okay, which give me some positive value of z, but we already know that z is a negative. Because of the symmetricity, we get this z is positive, but here in our case z is negative, so whatever z you get, then you have to add this minus sign here. Okay, so this your z is minus 1.64, as we know that z is negative. Here I get from the table as a positive value of z, but which is we get because of this symmetricity. Okay, so here your z is minus 1.64. You have to look at this table, 0.45. Okay, I show you in table 0.45. So 0.45, which I get, see, this both are the equal distance, 0.4495 and 0.4505. So I consider this 0.505. Now 0.4505, it means 1.6. This is 1.6, and then we have 0.05. So okay, so I have, okay, I have considered less one. This is 0.4495. 4495. So 0.04. So before the value of 0.4500, which is 0.4495, and 1.6, 0.04, 1.60. Okay, 1.64. I get 1.64. Okay, but see, this 1.64 which we get from the table is a positive value, but we already know that z is a negative. Because of the symmetricity, we get 1.64, but at the end z is negative, so therefore z1 is minus 1.64. Okay, z1 is minus 1.64. Now z1 is equal to c minus 120 upon 10. Okay, here standard normal variant z1 is, so, and z1 is equal to c minus 120 upon 10. So z1 is equal to minus 1.64, c minus 120 upon 10, and then after simplification I get c is equal to 103.6. So is it clear for everyone? If you have any doubt, you can ask right now. So previously we have discussed for p of x greater than c, and this one is p of x less than c. Is it clear? Okay. So now example number 6. assume that the mean height of Indian soldier is 68.22 inch with variance 10.8 inches. How many soldiers in the regiment of 1000 would you expect to be over 6 feet tall? Okay, so average height, mean height we have given of Indian soldier is 68.22 inches. Okay, and variance sigma which we have given 10.8 inches. Okay, and over 6 feet. So this 6 feet we have to convert into inch first of all. Okay, and this mu 68.22 inches, and variance we have given sigma square 10.8. So from the variance we have to find out the standard deviation, and number of soldier here 1000, and capital N we have given 1000. Now z is equal to x minus mu upon sigma. Okay, so how many soldiers in a regiment of 1000 would you expect to over 6 feet? So x greater than 6 feet. So 6 feet it means 72 inch. Okay. Okay, 1 feet it means 12 inch. So 72, 6 feet it means 72 inch. So x greater than 72. We have to probability of x greater than 72. We want to find out probability of x greater than 72. So first this 72 x1 we convert into a standard normal variant. So x minus mu upon sigma. So 72 minus 68.22 upon 3.29, in which I get 1.15 here. So now we are looking for x p of x greater than 72. So and 1.15. So z greater than z1, z greater than z1, and z1 is 1.15, 1.15. Okay, so all z greater than 1.15. So how we can find out for z greater than 1.5 all this area? So we know that all these regions over the y-axis, right hand side of y-axis is 0.5, and I can subtract from 0 to z in between 0 to, so area between 0 and 1.5 under the curve 0 and 1.15. Okay, so z in between 0 and 1.5, subtract 0.5 minus probability of z greater than equal to 0 less than equal to 1.5. So 0.5 minus, now from the table you have to find out this, you have to look for 1.15. Okay, in table see 1.15, how to look in table 1.15? So this is 1.1 here, 1.1, and for 0.5, 0.05 here. So what I get is 0.05, this is 0.3749. Okay, 0.3749. Okay, so here you can see that 0.3749. So 0.5 minus 0.3749. So I get p of x greater than 72 is 0.1251. So how many soldiers now of 1000? Okay, now we have to multiply this n, capital N, from 1000. Okay, so now expected number of Indian soldiers having height more than 6 feet is n into probability of x greater than 72. This one which we have find out for individual. Now we have out of and we have 6000, sorry 1000 in one regiment. So 1000 into 0.1251, and which I get 125.1. So approximately 125 soldiers which have out of 1000, 125 soldiers which have height over 6 feet. Okay, more than 6 feet. Is it clear for everyone? Is it clear? Okay, and see, clear, fine. So here we stop this our session, and we are going for practice sessions. Okay.